Welcome to Amdahl's law, the key idea that explains why adding more processors doesn't always make programs faster. To feel this intuitively, let's start with a simple highway analogy. Picture a wide multi-lane highway where cars cruise smoothly at full speed. Suddenly, the road narrows into a single-lane tunnel, a bottleneck that only one car can pass through at a time. Cars continue smoothly toward the tunnel, each one following its own lane. But no matter how many lanes we had before, everyone must merge into one sequential line at the tunnel. One by one, each car waits its turn and passes through. The wide highway collapses into a single file queue. And here's the real insight. The whole trip is limited by the slowest part, the bottleneck. Adding more lanes before the tunnel won't help if the tunnel stays tiny. Now let's convert this intuition into the actual math behind parallel computing. Amdahl's law helps us calculate the maximum speedup by balancing the parallel and sequential parts of a program. Smax is our best possible speedup. 1 minus p is the sequential part that must run alone. P is the parallel portion, and n is the number of processors we throw at it. With one core, imagine the program takes 100 seconds. 20% is sequential, shown in red. The remaining 80% is parallelizable, shown in green. Now let's crank it to 1,000 cores. The sequential 20 seconds stay exactly the same, but the parallel work shrinks to almost nothing, just 0.08 seconds. The surprising result? Even with 1,000 processors, we only get around a 5x speedup. As n grows, the sequential part dominates. That 20% cap becomes an iron ceiling. So where do these unavoidable sequential parts come from? In real programs, several common patterns create these sequential bottlenecks. Here are 6 major causes that limit your speedup. File I/O. Reading and writing data often happens one operation at a time, constrained by storage speed. Memory setup. Allocating or initializing large structures usually must run in order, not in parallel. Dependencies. When one step depends on the output of another, the chain forces sequential execution. Aggregation. Combining results from many threads is often a serial reduction step. Locks and synchronization. When threads share data, they must wait for exclusive access. Network communication. Distributed tasks must wait for data transfers, creating latency-driven bottlenecks. These patterns resist parallelization. They define the true ceiling on how fast your program can ever go. With these limits in mind, the next step is figuring out what part of the program to optimize. Here's the key question. What part should you actually optimize? Consider a program with 20% sequential work and 80% parallel work. Amdahl's law tells us this caps our maximum speedup at 5 times, regardless of how many processors we add. Many developers tend to optimize the large parallel portion first. They think, if I make this 80% super fast, I'll get huge gains. So they optimize the parallel work until it's nearly instant. Watch it shrink to almost nothing. But the ceiling barely moves. The sequential part hasn't changed, so the maximum speedup is still limited to 5 times. Let's reset and do this the smart way. The secret is simple. Attack the sequential part. Even small improvements here have massive impact. Reduce the sequential fraction from 0.2 to 0.1, and your ceiling doubles from 5 times to 10 times. By improving just the bottleneck, we dramatically raise the maximum possible speedup. That's the real leverage point. The takeaway. The sequential fraction is the true enemy of parallel performance. Fix the bottleneck, raise the ceiling, and let Amdahl's law guide your optimization strategy.